So far, we've been dealing with proportions, but now I want us to look at how we can do the same thing for means. So how are we going to calculate confidence intervals for means? Well, first, let's just go over a little notation. When we're talking about the parameter mean for the population, we would give that as the symbol mu. But the sample mean is the symbol x bar. Similarly, with the standard deviation, the population standard deviation is that Greek letter sigma, but the sample standard deviation is just S. What we'll do for these is a very similar process. We'll calculate, or we'll obtain a simple random sample of a particular size, and that population has some population mean and some population standard deviation, but we don't know it. What we can find out with the sample is what the sample mean is. And there's three things that will be true. The sampling distribution of that x bar will be normally distributed as long as n is relatively large. And in this case, n usually has to be about 30. The mean of the sampling distribution, this is going to be centered around that true unknown population mean, but the standard deviation here, it's going to be a little bit smaller than the standard deviation of the typical normal curve. It's going to be sigma divided by square root of n. Now, we don't actually know sigma, so we are going to have to estimate that, but that's okay. We can estimate it with the sample standard deviation. Because this is just an intro survey course, we are not going to spend much time on what's going on here, but it pains me a little bit to not spend much time on this idea. But why is it that we can use this normal distribution? Why is it that we can do this? Well, it's because of this thing called the central limit theorem. And what that central limit theorem basically says is that as we take more and more observations from a population, then the distribution of the mean is going to get close to a normal distribution. So as long as you take enough observations, as long as your sample size is big enough, we are in fact allowed to do this process. Now, it takes a lot more math to prove this, but just rest assured that we can in fact use these methods from our samples. So how is a confidence interval for a population formed? Very similarly to our proportions, we're going to take our statistic, our x bar, and then we're going to determine how many standard errors that we need to go, and that's going to be based on our confidence interval. This is going to be done in technology, so we don't have to worry about how to find it. And then we'll have our standard deviation divided by the square root of n for our standard error. So if we wanted to decrease the size of our standard error, if we wanted to make a narrower window, then you would have to take a bigger sample size. But it is worth noting here that it's divided by the square root of n. So it would take a quadrupling of your sample size to have half of the width. So it's not going to work. If you double it, you get a half. It doesn't work quite that nicely. So you do have to take a really big sample in order to get a narrow confidence interval. So how do we do this? Well, let's see. This example says, fire the coach. A college president says 99% of alumni support my firing of Coach Boggs. You contact a simple random sample of 200 of the 15,000 living alumni, and you find that 66 support firing the coach. So what's important here is the size of the sample and how many of them are a success. I don't actually need to know that 15,000. And I don't even need to know what the president said because that's not relevant to what I'm doing. So who are we interested in? We're interested in the college alumni. All right, we at least need to know where it came from. These are from college alumni. So what is it that this question is asking us for? It's asking us for the population proportion. Here, this would be the proportion of all alumni that support firing. It's important that we recognize that this is a proportion question, and the way we know that is because we were given a sample and we were given how many people agreed with the statement. So that's a proportion setting. So what is our p hat? It's going to be 66 divided by 200, which is 0.33. That's a lot less than what the president said. So let's go to Crunch It and do this calculation. So I'm going to go to Statistics, Proportion, One Sample, and I'm looking at 266, and I am going to do a 95% confidence interval. And so my confidence interval is 0.2643 to 0.3952. So based on our sample, we are seeing that somewhere between 26.5% and 39.5% of all alumni support firing. So if our confidence interval is correct, the president is way off. Now, it is possible that we just contacted a strange group of 200 people, but the more likely scenario is the president was incorrect. Example 12 here is a question about gun control, where the Pew Research Center asked 1,507 adults whether they thought it was important to control gun ownership. A total of 693 said that they were in support of gun control. So, although these samples were not perfect simple random samples, it's still okay for us to do these confidence intervals. So what is the population proportion here? Well, one, we know it's a proportion because we're talking about how many in our sample. But what is it? We want to know the true proportion of all Americans that support gun control. So in order to calculate our confidence interval, we're simply going to go to Crunch It, go to Statistics, Proportion, One Sample, and we had 1,507, and out of them 693 supported, and we wanted 95%. And so our confidence interval is 0.4347 and 0.4850. So what this interval tells us is that, at least based on this survey in 2014, less than half of the United States supported gun control. So this kind of information can be really helpful for politicians, for policymakers, to get a pulse of what's going on in the country. Now, the Pew Research Center announced that the margin of error would be plus or minus 2.9 percentage points. So is that what we got? So how do we figure out our margin of error? So there's two different ways to calculate the margin of error. You can do Z star and then your P hat 1 minus P hat over N, or you can do your Z star times the standard error that you got in Crunch It, which is probably the easiest thing. And here our standard error was 0.01284. And we would multiply that by the Z star that's given in our notes for a 95% confidence interval. The Z star we use is 1.96. So if we multiply 1.96 times the standard error, we get that it is 0.025, which is close to what they said. Our calculation was 2.5 percentage points, but they were using something slightly more sophisticated than we were, but we have a very similar margin of error. But just as a quick review, to get the margin of error, it's going to be your Z star times that standard error that you get in Crunch It. Now, if we wanted the 90% confidence interval, we go back to Crunch It, and you need to do it again, proportion, one sample, and just change that to a 90% confidence interval. And we'll see here that we have a narrower interval, smaller, and the reason is because we weren't quite as confident. We were able to make a smaller target because we were okay with missing more frequently. Next two questions are dealing with means. The reason that we know we're dealing with means is because we were given information about the mean. Now, number 23 is not actually a confidence interval question, but it was a question similar to something in the homework. So here, this is going back to chapter 13, which is the normal distribution. So what is the middle 95% of all scores? Well, we need to go 1.96 standard deviations. So we could take our 18 and add 1.96 times that standard deviation, 18, and minus 1.96 times that standard deviation to get our answer. And that is giving us 6.242, and then 18 plus 1.96 times 6, 29.76. But here's where we're dealing with something new in this chapter. Instead of a single individual, we're going to take a simple random sample of 25 of these students. So this time it's 1.96 times our standard deviation, but it's of the sample. And what happens here is it's 1.96, and we'll do the standard deviation divided by the square root of the sample size. That's a little bit different, but here we're interested in the range that contains the 95% of the average x-bars. So we'll do 18 minus that value, and we'll do 18 plus that value. And it's going to take a little bit in my calculator. That gives me 15.648 and 20.352. So what is the implication here? That was a much narrower interval, and it was still a 95%. So what happened? Well, think about this. Individuals are going to have a lot more variation than the average of a group. When you average people, those extremes tend not to happen as frequently. So when we're looking at questions like this is how you'll handle these questions, and you will get something smaller when you're looking at the averages. And then finally, let's see how we do a confidence interval for the mean. So we've got a lot of information here. What do we need to know? The bank takes a simple random sample of 200. It compares how much these customers charged this year compared to the amount they charged last year. The mean increase of the sample is 346, so that's our x-bar. Our sample size is 200, and our standard deviation is 112, and we want a 99% confidence interval. So we take all of that information and go to crunch it. We go to statistics, and we go to Z. Okay, I know it doesn't say mean, but that's what we're going to use here. We go to Z, one sample. And we have to go to summarized because we don't have the raw data. What we know is that a sample size was 200, the sample mean was 346, and the standard deviation was 112. Now we're dealing with confidence intervals right now, and we wanted a 99, so I'm going to change that to 99 and hit calculate. And that tells me that the true mean is somewhere between $325.60 and $366.40. So we're 99% confident that the true mean difference is between those two numbers.